course, this is just an image. We want to study the whole simulation. We concentrate for a moment on that part over here. Okay? So, once again, now the idea with this diagram is I have a space-time problem, 4 dimensions. I want to reduce it to 2, and the idea is, once again, I take just this axis, the x-axis along the plane, because I know pretty much there's something happening in the back and it's traveling to the front, and that's the most interesting part. And that allows me, once again, to say, okay, 0 over here would be the top of the wing, that red corner. This is the end of the wing, and that's about 50% behind the wing, to give you an idea. And then you can see, once again, we have many time steps. There is one time step where this vertex burst is created. I can tell you which, pretty much, of course, the computer knows exactly the position, but I can tell you, well, you're about 40% behind the wing, and you can see what happens. It creates, it gets a starting, and then it starts moving above the wing actually. And that's what you don't like, because this rather chaotic structure there creates high pressure variations. This is a snapshot, but this is quite active. You saw that in this physical experiment, right? So you get pressure variations that are problematic for the structural stability of that plane. Also, this vortex here means low pressure above the wing, and for a delta wing, the lift basically is created. You have a vortex above the wing, meaning low pressure. Yeah, you know, typhoon means low pressure. Yeah, vortex, low pressure. And if you have low pressure above and high or the normal pressure below, you create a force that's creating the lift. Well, if that structure gets unstable, of course your lift gets unstable, and that's not funny for the pilot, to say the least. So you get danger to the structure because you have high forces, and also you use lift. So you want to avoid that, but on the other hand, if you're a fighter pilot, you want to take that sharp turn to essentially escape enemy fire or to do certain maneuvers. Okay, we saw that part. Now let's look at the other part. Okay, just forget once again about all the other curves that we put in later. Just look at that green thing. We're comparing 595, 597, pretty much the same time. And you see once again we're pretty much at the same position, and it's traveling, but suddenly something else happens. So you have additional critical points. The structure is different. And if I show you this nice transparent stream surface here, you can see this looks different than that one, right? And now the funny part, which some people are still interested in, is, of course I can compare, right? There's a slight difference, but the similarity on both sides, to some degree, is the same, and it cranks up later. You can pretty much see that on both sides. So you could start studying this phenomenon based on this. And again, since we are the computer scientists here, it's not very difficult to find the zeros in a vector field. You could imagine, right? Even if I have a tetrahedron and have a linear equation, it's pretty much solving a linear equation in each cell. That's not going to be very hard, but it's powerful because there's a connection to the physics, to the engineering, to the aerodynamics problem. That's of course important here. So we see that vertex burst analysis can be done by tracking critical points. The complexity for the computer scientist is linear in the number of cells and number of time steps, because for each cell it's a simple problem to find that zero. It's obviously a parallel problem if I do something in all cells and all time steps without many connections. So that's fast and suitable for large data. You cannot be much faster than linear anyway in your data. And you have a qualitative and quantitative analysis of critical point evolution. Now, I guess you were interested in aerodynamics. I hope you're also interested in health problems, especially if they are, once again, connected to fluid dynamics. So, a short notion well, this topological vector field visualization partitions basically the flow into parts with similar behavior using topological considerations. I hope I made that somewhat clear in that introduction, right? You have the whole domain, and you just split it into areas where vector field behaves, where the streamlines go in different directions. Well, being a computer scientist, I can think, well, I can partition all my streamlines or path lines also based on other properties. Yeah? You give me a property that I can calculate, and I can say this path fulfills the property, this one doesn't. You just need a logical predicate. Right. So I can do that a lot more general. The question is, how do I come up with nice predicates? Now, let's switch to medicine, for example. You probably have heard about magnetic resonance imaging. It's a famous imaging method in medicine. Any clinic probably in the world, I'm sure also in Japan, has one, even many doctors. And you can create nice pictures of the anatomy without cutting it open, right? Which is not so nice for the patients, yeah, just to look inside. And the magnetic resonance imaging is very nice also for all the kind of soft matter. Yeah, if you take computer tomography, that's nice for the bones, but for the soft structures, this is one way. But there is a variant, and that's four-dimensional phase shift, or phase contrast actually, that allows you to calculate the velocity in all 3 dimensions. And here, of course, we're interested in blood flow. So what do we do? Well, we synchronize imaging with your heartbeat, and then we're able to create an image every 40 milliseconds. And if the heartbeat is about 1 second, 60 beats a minute is a decent heartbeat, right? If you are lying there quite relaxed, you're not doing sports at that moment. And then I get about 25 images, and I repeat them synchronized with the heartbeat so that I get kind of a smooth image to smooth out the error. Simple trick. And then I can calculate the vectors. So what's the interest here? Well, cardiovascular diseases are based on morphologic, so changes of the blood vessels, and hemodynamic changes. If you don't know hemodynamics, that's basically error of fluid dynamics for blood. Yeah? And cardiovascular diseases, I don't know exactly about Japan, at least in Germany or Europe and also in the US, it's the major cause of death. Yeah? So a lot of people are interested here. Yeah? Whoever has any kind of heart problems, eaten too much Western food, not enough fish and sushi, develops this kind of problems. Yeah? So you, and PC-MRI is now interesting because it allows measurements of 3-dimensional unsteady blood flow in vivo without doing any harm to the patient except for the magnetic fields. So the medical doctors are interested in the distribution of velocities of paths of the flow, residence time, and vortex generation. Because all this interacts with the morphology and the body adapts, right? And you want to see if things are okay or not. Well, if you go to the big manufacturers, of course they have these protocols out there, but so far typically it looks like that. You can have a plane there and see where all this blood goes in there. You can have another plane, and then you can see, and this is a very pulsed flow because you have that heartbeat, right? You have fast flow and slow. Yeah, but this is user dependent and it's time consuming, so we want to get a better insight. Well, our idea is path line predicates, so we want to have logical expressions based on the path lines. And first of all, we calculate a dense number of path lines. Yeah, we have gridded data, Eulerian description, if you want to be a physicist. And we're changing into a Lagrangian description with many path lines. Basically, for the computer scientist, we have all these little cells and make sure that in every time step, we have at least one particle in each cell. Yeah, and for computer scientists, obvious what you have to do, right? Just sample dense enough, and you're going to be fine. Yeah. So we pre-compute all these path lines, and then we just calculate our predicate and select the ones that fulfill the predicate and discriminate them from the others. When we have several predicates, we get a lot of partitions. The path line predicate is simply a Boolean function. It's true or false if the path line fulfills the condition or not. And if you went to your theory, logic class, or math class, you can also create some nice formulas. But the idea is pretty clear, I guess. So how does the workflow look? Well, there's a pre-processing. You get the imaging data. You do a segmentation because you're interested, of course, in the large vessels or the heart. We look at the aorta and the heart. We can't look at the small vessels because the resolution is not high enough. Yeah, it's just a question of measurements here. Then we do this path line computation. Yeah, it also means only in this area here we have realistic velocities. Yeah, but it's not zero outside. There's a lot of noise. Yeah. And then we also have vortex detection methods that tell us where in the flow we might have vortices. And then we have the user, he can use a combination of this path line predicates, gets an image, may get inside new questions, and if you are in a research cycle, he may look into new predicates. That's the visual analysis part here. And you see we're somewhat away still from the hospital. Now, some predicates. Well, I told you it's a pulsed flow. So one interesting thing, of course, would be to look for the fastest parts. And that's not difficult, right? If I have my path line, I can calculate all the velocities. I can just sort them and find out which particles are faster than the others. So take that 10. Fastest 10% is not a difficult task by any means. I can just show these streamlines to show where is the flow fastest and where does it go. Yeah, does it look? Yeah, and I can identify jets. If this is my aorta and the heart would be here and then it goes like this, and normally it's supposed to go down and support the main body. But there are a few parts, and you see here the quality or problems in the segmentation because we have that limited resolution. But there are some arteries that go up to the head. And now, of course,